Hello everyone. Is everyone present? Can we start? Okay, there's one thing. Okay, before we start, can we close the window, please? Thanks. Uh, there's a few things that I wanted to talk about in the previous lecture, but forgot about them. So I'll just be really quick about them. Uh, I wanted to talk about how noise is generated. Remember the noise function that took uh, two coordinates and output another one. Basically what this does, let's assume all these are integers. Basically it takes the x value in binary, like 0, 1, whatever. It takes the y value, the z value in binary. It shifts the z value, not shifts, it rotates the bits. So it takes rotation, so the value actually is like this. And then it uses an XOR operation bitwise. So this bit with this bit like this. So it produces some binary number. And finally, it adds some large number to it just for effect. So basically this means that for the same x and same z, you get the same y, and yet when you change a single bit in x or single bit in z, the returned number changes dramatically, which is quite a good property of the noise. That's also the reason why we are using integers, because it wouldn't work with floating point numbers. It works with integers only. Okay. Second note, I talked about how the noise, when we do it in integers, and then we interpolate it, but it's still too smooth. Sometimes we want a little bit more variation, so we take a noise like this. Let's say it's fxz, and we add another noise, f1 and f2, and we use coordinates that are multiplied by a large number. Let's say 10, for example, 10x, 10z. What this does, also we multiply this by a scale factor. What this does is actually it takes this curve and adds a little wiggle to the curve. We can add in a few more of these terms, each with a different frequency and scale, and that's what's called the Perlin noise. Perlin was the guy who invented this kind of noise. So now when we say Perlin noise, you know what to expect. This is in 2 dimensions, of course. We can make multi-dimensional noise, so it can be x, y, z, etc. It can be done in a number of dimensions, but the more dimensions we add, the slower it is to calculate. So 3 dimensions is the most we use for Cuberite. One more thing that happens to Perlin, usually the noises oscillate around 0. So this is actually the 0. And if we take absolute value, So the graph generally flips these parts over to the other part above the axis. That's called ridge multi-noise. And it's great for generating mountains, as we will see in a moment. And the third thing I wanted to mention, mountains. Okay. Third thing, most of what I'm talking about is already available in the Cuberite repository in the documentations folder, and it's also online, so I'll be sending an address right now. There it is in Mumble. Maybe Julian can copy it to the Twitch stream. From Mumble, yeah. So these are the three things I forgot about in the previous lecture. Now let's continue. Wow. The green one is nice to see, but it's difficult to erase. So next up, we have Terran Height generators. Although we have rendered them obsolete, there are still a few that come in handy, and they can still be used in the composable generator pipeline via a bridge. So let's say the basic one is of course no height at all, flat, which means you choose a height and all the world the same height. Not very interesting, but even vanilla Minecraft has it, so it is for some uses, mostly testing. Second one is so-called min-max. What this does is it uses a Perlin noise, which we've talked about right now, and it says for each biome it has a value of minimum and maximum height for that biome. So it says for mountains, go from here to here. For rivers, go from here to here. For plains, go from here to here. And the noise generated, the Perlin noise is generated so that it matches these ranges. Then, of course, it wouldn't work well if there was a biome boundary. So if there was a river biome going through mountain biome, then we would have a step like this. That wouldn't be nice. So actually, this does some form of averaging. Which means it takes a 5x5 grid of biomes. This is X, this is Z. This is the column that is queried for height. So 5x5 columns around it are queried for biomes, and the minimum and maximum parameters are averaged around. So although this says river, this says mountain, the averaging says, okay, this is 1/25th river, 1/25th mountain, plus something else. So this actually does some smoothing around the chunk borders, which is exactly what we want to do. This is mostly all about the min-max. It's not so complicated. Oh dear. Next one It's called the Biomol, whatever the pronunciation is, which means dependent on biomes. It works somewhat the same as the min-max, but instead of modifying the minimum and maximum, it modifies the actual parameters of the Perlin noise. You remember the Perlin noise had a scale and the frequency. So each biome defines its own set of scales and set of frequencies for the Perlin noise. And again, on biome boundaries, it's averaged. Or rather, it's averaged everywhere, but on biome boundaries, it's the most, you can see the most. So Biomol is pretty much the average. It's about the best Terran height that we had until we started using the Terran shape. There's two more generators in the Terran height category that are somewhat interesting. There's a mountains generator that doesn't use biome information at all. It generates mountains everywhere, but what it does is it uses the ridged multi-noise, which generally looks like some easy slope, then up and back down, slope and up and down. That's what ridge multi looks like in Terran Height. And it uses two of these. The other one is inverted with a different seed, so it looks different, and the peaks are downwards. And it uses another noise to actually make a weighted average of these two noises. So the resulting height is something like this. So as you can see, it's mountains and valleys mostly. Unfortunately, this one doesn't work well with biomes, and it's quite difficult to make it work with biomes. So it hasn't been updated for that, and we don't use it much. But it's a nice little experiment, and for some servers that use mountains only, it could be a nice thing to have. Wow, the board is taking a beating. Of course, the Noise 3D generator belongs to the next category. Don't worry. I hope I can make it in time. The last Terran Height generator is the Steppe, which was an experiment from my side, inspired by someone on the forum posted an image of Japanese-looking mountains, and it was. If I draw it in 2D, it was this kind of steps as mountains. And what this generator does, it actually uses the same technique as the grown biomes. It uses an array of integers, and instead of interpreting them as biomes, it actually interprets them as terrain heights. So it uses the zoom, the smooth, and everything we talked about last hour. And as the last step, it does a little bit of height averaging so that these are not too sharp. But generally, it's the same technique used for the grown biomes. And it works pretty well, but again, it's not working too well with biomes. So unfortunately, that's a single-purpose generator. Right. So now we get to the really advanced stuff. Okay, question to Steppe. let's hear it, or rather, let's read it. Thanks, Nilspace. That's most likely the link I was referring to. No, the thing in the middle would actually be either 1 or a 3. So, the question is, if you have 1, 3, 1, 3, and you apply the zoom in the grown scheme, you would get 1, 3, 1, 3. This would be a 1, this would be a 3. This could be either 1 or 3, so let's choose 1. This could be this one could be either 1 or 3, so let's choose 3. And this one could be either of the corners, so let's choose 3, for example. So this could be one result of the zoom operation. So no, the point of the grown generator is it doesn't average numbers, it uses the same numbers that are already present. Maybe worth noting what the zoom operation finally does. If repeated several times, it generates blobs like this. And each blob has same number used in it. So that's exactly what the biomes we want, and that's exactly what the steppe Terran Height does. Each of these is a different height in the steppes. Right. You're welcome. Doesn't help much. Perhaps later on. Okay, so that would be Terran Height. I should get rid of this as well. It might have been a good idea to actually take pictures of the whiteboard before I erased it. Well, too late now. Right. Okay. Let's hope it's readable on the camera. I really hope so. My writing is really bad. Okay, terrain shape. So, unlike the previous generators, we don't have really easy one, because we don't want an easy one. We already covered the easy ones in the previous ones. So, what we have is, the first one is a bridge that bridges the terrain shape to the terrain height. So this means that the shape of the terrain is built from a terrain height generator that is still running in the background somewhere. There's not really much to say about it. The next one is distorted Heightmap. This was the first attempt at generating overhangs in Cuberite. This works by saying, okay, so let's take a height map represented here as this curve. So this is y, this is x or z. And whenever we get a query for a chord here, and a height here, because we have a query like f, x, y, z, so we get a query here, we apply a little bit of noise on each coordinate and then check whether it's less than or more than the height. So in a math form, it would be noise 1 XYZ, noise 2 XYZ, noise 3 XYZ. All these would be fed into another noise. So that's basically a lot of noise, and it takes quite a lot of time to calculate all this. So this was a really slow generator, and it didn't work so well. So we had to come up with something a little bit more optimizable. Of course, the natural choice would be 3D Perlin Noise, which is called just Noise 3D. This is exactly what NilSpace was asking about. And this is just a simple function that says for each x, y, and z, take the direct noise returned value from those coordinates. And if it's larger than 0, it's land. If it's less than 0, it's ocean. Unfortunately, it can't work this simply, because calculating noise for an entire chunk, which is 16 by 256 by 16, which is more than 65,000 values, this is a lot of calculations. So what we do instead is linear interpolation. And we are even better, because interpolation is still slow. We do upscaling, which is a subset of the interpolation when we know that we are upscaling by an integer number. So what we do, instead of choosing all the 16 by 256 by 16 blocks, we only choose 4 by 16 by 4 blocks. For these, we calculate the noise function. So we get the values, and then for, which means let's I'll try to draw it in 2 dimensions. So we have a chunk that is 16 by 16 blocks. We want to calculate a noise function for this entire thing, but we don't want to calculate everything. So instead of going 16 by 16, we go only by 4 by 4. And then for the rest, we use linear interpolation. I suppose most of us know what that is. Linear interpolation means you have 2 values, so you draw a line along them, and that's exactly the values that you want to get. So this works in 2D, and it works in 3 dimensions as well. And it minimizes the work so much that this is actually it can be used as a generator. One problem with this approach is that the 3D noise actually would generate kind of a sponge, because it doesn't have a concept of floor, ceiling, that there should be a sky, there should be a ground that is all solid. So what we do, we don't take the noise value as it is, but we add a little bit of y coordinate. This means that okay, for this we need to actually subtract so that this stands. This means that the noise value, the noise, if I draw it in a graph, doesn't go like this, but instead it goes like this. So whenever we choose a threshold, which means here's air and here's land. Whoa, I said ocean here. Okay, so when we say this is upwards is air, downwards is land, it means that this noise actually generates air the more up it goes. I hope this is understandable. Okay. This is getting too technical, and it's still not the best generator, so let's not dwell on this. Let's move to the better ones. We have a thing called Biomol Noise 3D, and it works similar to Noise 3D, but the noises parameters, the amplitude and the scale and the frequencies are chosen based on biomes again. So this means that we can actually modify the parameters, and it works so that extreme hills actually are hills and the rivers are rivers. It works this similar way like previously in the Terran Height I mentioned Biomol versus non-Biomol. It's the same. Nothing much to it really. And the Biomol Noise 3D is actually the currently best shape generator that we have, and it is the one used by default in Cuberite. Okay, next one is called, what is it called? Right, 2 heights. Or is this one the default? Can't remember now. 2 heights is right. That's not a question, that's a praise. Thank you. 2 heights generator. This is something of a beast. That's quite difficult to explain, so I'll try my best, but still what it does is it generates 2 height maps, one height map, another height map, and then it generates a 3D noise, and based on the 3D noise's value it chooses either the first one or the second one. For each column, for each block in the chunk, it generates a 3D noise and then asks which height map should be used. Despite what it looks like, it uses height maps, but still this can provide overhangs. And it does, and I think that 2 heights is actually the default now because it's the best. And if I remember correctly, this is actually what vanilla Minecraft uses as well. So, if I were to write it in math terms, this would probably be the formula informally written. So based on the noise, 3D noise value, if it's more than 0, use one height map. If it's less than 0, use the other height map. Note that this value depends on the y coordinate, so it actually does provide a density instead of a height map. And the last one is the end. This generator is used for the end, and it's for the end dimension of Minecraft, and it's basically a 3D noise that uses a distance from the spawn as part of the noise. So the further you are from the spawn, the less density you get, until at one point the density is always 0. There's not really much to it, and unfortunately I think it's broken right now in Cuberite. I'm not sure, so I might have a look at it and fix it someday. But basically it works as noise 3D, nothing else. That would be all for the Terran shape generators. I just hope you can see this. Okay. The end in 1.9 in the upcoming release of vanilla will need updating anyway, so we'll probably get rid of the end generator and program a new one. Since it's not working, it won't matter if we change it. Okay, the next part is terrain composition. Up until now, we have decided which blocks are solid and which blocks are air, but we haven't specified whether the solid blocks are sand, gravel, dirt, grass, whatever. So that's this is the task for the composition generators. And mostly there's just there's not much to do about composition, really. Either you make it as close to vanilla or not. So there's the first one is for debugging purposes, of course. So it's same block. Which basically means it keeps all solid blocks as stone or whatever block type you choose, and it's meant to be as fast as possible, so that when you're debugging another part of a generator, that this one doesn't slow you down. Because still a composition needs to be present, some kind of composition needs to be present, so let's make it the easiest one possible. The next one is debug biomes. Another debugging composition generator. Basically what this does, for each biome it chooses one block type and it fills the entire biome with the block type. Each biome gets a different block type, so that when you have a map or a tool that displays the world, you can easily see the biomes in the map. Again, quite a fast one. The end and the nether are more or less the same. They just fill the entire solid blocks with endstone and netherrack, although they add the bedrock. Wait, the end doesn't. Only the nether adds the bedrock on top and bottom of the level. Doesn't do much else. Then there's classic. That's a composition generator that predates even me in the Cuberite project, and it's still kept alive. So as you can see, we keep backward compatibility quite a lot. What it does is quite simple. Let's say you have a terrain like this. That's X or Z. This is Y. And it uses a concept of sea level. So this is a sea level. Anything up until a little bit above sea level, this little thing is a beach. So it gets sand on top, dirt, a little bit of dirt underneath, and finally stone. All above this level gets plains, or plain-like composition, which means dirt on top, grass on top, a little bit of dirt and stone. Everything below the sea level gets water, dirt, and stone. Nothing more. So that's the classic one. And the last one that is actually used most often is the Biomol. It's the default and it's the best we have currently. It works somewhat close to the classic one, but it takes biomes into consideration. So deserts don't get the grass and dirt on top. Instead, they get sand, and it has ocean floor. Gets a selection of either it can be sand, it can be clay, and it can be dirt. And it uses 2D Perlin Noise to choose between the three. So for each column of blocks, the 2D Perlin is queried, and if the value is very high, it uses clay. If it's above 0, it's sand, and if it's below 0, it's dirt. Nothing else. So the ocean floor actually gets a nice kind of zebra-looking pattern based on sand and dirt and clay. Okay. Do we have questions? The last 5 minutes. Oh, sorry. You need to watch the Twitch again. I can't really go back because I'm running out of time. The last category is finishers. And there's a whole load of them. So I've actually decided to just skip through some. There are some that are simple, just like animals, glowstone, ice, pre-simulator, snow, springs, etc. They just usually take one block and change it into a different block, such as the ice finisher makes sure that every water on top of the terrain is turned into ice. The springs finisher takes a block in a wall, so that that's a solid block next to an air block, and it changes the solid block into a water spring or a lava spring. What could be interesting is the nether clump foliage. This was actually done by Niels, not me, but hopefully I can explain how it works. For each chunk, it chooses a point x, y, z, and from that point it chooses several close-by points. So it makes like a star in 3D space. And then in each of these ends of the star, it places the foliage, be it mushroom, be it fire, whatever is needed for the nether. And this actually makes it look like the mushrooms grew in a bunch together. So it's really a bunching algorithm, nothing else. It chooses it produces several of such suns in a chunk, each one for a different block that should be generated. We should get a similar finisher for the overworld as well, because right now there's nothing like this and it's missing. So Niels, you know what to do. Okay, let's skip the simple ones. Then there's obsolete ones. I'll just write them down anyway. Direct overhangs. This was an attempt to make overhangs before we had the shape generators. So pretty much with the Terran shape generator, this one is obsolete. I have no idea if it worked well or not. I can't remember really. But I think it did work, because if it didn't, I wouldn't commit it. Next one, dual rich caves. This was a pretty interesting generator, but didn't work out so well. It used several 3D Perlin and multi-rich noises to produce caves. I don't want to talk about the details because it doesn't really work so well, but the resulting caves were large labyrinths and they were all interconnected. Unlike caves in Minecraft, which are somewhat separated, this created caves everywhere, basically. They were not much caves, such as more crevices and cracks in the terrain, etc. Next one was marble caves. This was similar. I don't have exact recollection of which one is which, but they both produced similar looking caves and they didn't work so well. I think the marble caves actually, when viewed from the top, they were like zebra stripes. So caves everywhere and it was not looking so good. And the last one, ravines. This one was actually obsoleted because we have a better ravine generator now. It's called rough ravines. This one had smooth. This one produced smooth ravines, which means the ravine, when viewed from a cross section, would look like this. that's not much of a ravine. Nowadays we have ravine generator that can do little steps like this, so that it's interesting a little bit more. So these are the obsolete ones. Let's get rid of them. Okay, now we're going for the advanced ones, and they are the reason you are here, right? uh, so let's start with simple ones first. The simple advanced ones. Dungeon rooms. It's pretty straightforward what this does. It picks a location somewhere in the chunk and generates a room around it, and puts a dungeon in the middle, puts a spawner, monster spawner in the middle of the room. Nothing else. The problem this generator still does have is sometimes it generates mid-air, so doesn't work so well, but still better than nothing. The next one is pretty much the basis of all the advanced stuff. Grid structure, can't write. Structure generator. That's not actually a generator that you can choose because it's a base class from which multiple generators inherit their workings. So it's like providing generic behavior on which other generators build. What it does is it takes the X and Z space and divides it into a grid. And in each grid, one point is considered the seed of the structure. The structure can be anything in this case. We'll see later what the structures are. This looks familiar, doesn't it? It is almost the same as in the Voronoi diagrams. So that's basically what the grid structure generator does, and the structure. One important property of the structure of the generator is that for any given chunk, let's say this is the chunk, there's only a limited number of grid cells that can be inside the chunk. And this limited number is very important because that's what allows a lot of optimization for later generators. Okay, I'll have a look at my notes if there was anything I wanted to tell. Oh yeah. So, what's the grid structure generator used for? Mine shafts, peace structures, ravines, rough ravines, and worm nest caves. All of these actually use grid structure generator underneath. Okay, let's move on to the next finisher, and we'll get back to this when we actually visit one of the instances. So the next one is lakes. This is one of the easier ones. Just like dungeon rooms, it picks a random spot in a chunk and generates a lake around it. A lake means I think 3 or 4 bubbles next to each other. Each bubble is generated randomly, and each bubble is okay. This is an XZ view. In a cross-section view, all the bubbles are at the same height, so it's like this. Uh, and the bubbles are filled with whatever fluid, either lava or water, in a half. So this thing is actually imprinted into the chunk, and that's just a lake. As simple as that. Next up, I don't like these two. Ore nests and ore pockets. Yeah. The pockets are added recently, but doesn't really matter. Um, each of these two has a list of ores that should be generated, and for each ore they generate what's called either a nest or a pocket, basically the same thing. It tries to make a little clump, whatever, a little clump of the ore blocks next to each other. The ore nest does this by picking a point and then walking the neighbors. So it says, okay, x plus 1, z plus 1, x plus 1, x minus 1, z plus 1, x minus 1. And it generates this set of points. And for each point, it replaces the block at that point with the ore. Because the blocks are next to each other, it looks like a vein of ores. It actually is a little bit smarter than that, because each point gets a radius. So this one says small, this one says large, etc. But still, even the smallest one is larger than the distance between the two points. I didn't want to draw it that way, but I guess you get it. The ore pockets looks very similar, but instead of doing a random walk, it chooses one point, another point on a line, and then does something like this. So it makes circles around points on that line. Let's say this is 6 blocks. This way, the ore pocket is somewhat larger than the ore nest. It is more together, but still, it's just ores. All right. Next up. Yeah, it's unfortunately it's not getting erased so well, but let's hope you can still read it. I'll keep this one as the last one. Let's go to rough ravines. That's one of my personal favorites. Okay, so how do we generate a ravine? We take a top-down view, so this is X, this is Z, and we pick several line segments attached to each other. So we go like this, this, and this. That's the base of our ravine, the base shape. Overall, this could be like 100 blocks, just to give you the idea of scale. What it does next, for each segment, it removes the endpoints and instead replaces them with quarter points. So this point is taken, this point is taken. For the next segment, this point, and the last segment, this point, and this point. So After one iteration, we have line. Okay, this won't work. I'm sorry, it's gonna be green on green. So we get a line that is somewhat smoother than the original. Then again, we do this again. Quarter points, quarter points, quarter points, quarter points, etc. And finally, we get a shape that is pretty smooth. That's the basic shape of the ravine when looked top down. Also, at the same time, each point gets a radius. So this one says radius 1, radius 2, radius 3, radius 4. And whenever we divide the line, we actually linearly interpolate the radius. So when the radius was like this and this one was smaller, so we interpolate the radii like this. So when we have the final smooth shaped, we also have the radii around it that go like this. Now it's starting to look like a shape of a ravine, really. And that's exactly what the smooth ravines, the old one, was doing. It just took this shape and bore it into ground. Smooth walls, nothing else. Rough ravines is a little bit more complicated. It has a little bit of a lookup table for X and Z. That's not really X and Z, it's more like radius, dependent on height. So it provides steps like these. And this is the actual wall that is being imprinted on onto this ravine. So basically, this is what's getting generated into the terrain. I hope this is understandable. Okay, next one. Whiteboard looks like a zombie. Brains. Okay, next one is south end rims. We should get Nils really explain this one. Basically what it does in a cross section, so it's X or Z, this is Y, and we have a nether, which means basically we have huge caverns, bubbles, like Swiss cheese. And southern rims takes points that are thin enough and replaces the nether rack in such points with soul sand. So this will get replaced and this will get replaced, nothing else. Additionally, it uses a 2D Perlin noise to decide whether to replace it or not at all. Is that so, Niels? Okay, next one. This one's not so interesting, really. Sorry. Next one is the trees. This one's pretty straightforward. It picks an XZ point. Uh, from there it gets the topmost block's Y coordinate, so it has a point in space. And for this point, a tree is chosen based on biome. So each biome has a list of tree images that it is using, and it picks one tree image from the list and it puts it there. What's important is chunk borders. So if we have a chunk and the point lies here and the entire tree should be like this, we need to make sure that this chunk will contain this part of the tree. That's where this is one of the most important points for there being the generators are repeatable, because we need to ask for the shape generator of this chunk in order to be able to generate this chunk. Okay, I won't talk too much about trees because those are subject to change in near future, hopefully. Spoilers. We're getting to the good stuff. Worm nest caves. This is a good one. A difficult one, but a good one. It chooses a point inside the terrain, so it needs to know where the Terran Height is. It chooses a point. From there, it makes 3 tunnels in any direction, in any length. Each gets a number attached to it from 3 to 5, I think. Can we get light back, please? All right, technical issues, but those should be really easy to fix. Right, thank you. So, are we there? Are we ready there? Okay. Okay. So each of these lines gets a number. What's going on? Hmm. So let's say this one gets 3, this one gets 4, this one gets 5. At the endpoints, the lines split into a Y intersection, each in a different direction, and each having one less. So it's 2, 2, 3, 3, 4, 4, and 4. Damn. Sorry. This is repeated until the numbers on the lines reach 0. So there's one more, one more, one more, one more. So basically what this does is a kind of a binary tree with a trinary root. Each of the points is assigned a coordinate in a 3D space, and each line represents a tunnel that is then carved into the chunk. So actually each of these points is a cave branching off. Of course we don't want this to be lines, so the last step is turning the lines into some curves. Similarly as the rough ravines or ravines are turned from lines to curves, this takes a similar process. So that's how worm nest caves work. Next up, villages. I know we are already running out of time, so excuse me, but I'll continue if you don't mind. Villages. Um, they they inherit from grid structure generators, so they are based in a grid, and each grid has a seed in it, and the seed is the actual well. It's the well of the village or the city center, let's say. From there on, each well connects to roads, and each road connects to a house, or multiple houses, multiple roads. So if we have a top-down view, this is the well, there's a road, there's another road, and let's say this is another road. This road connects to a house, another road, etc., etc. The connections here are very important, and when I developed villages, I actually thought, well, these connections are pretty useful. We could use them not only for villages, but for other stuff as well. So the next generator that is somewhat similar to villages, but it's more generic, is piece structures. Think of it as villages on steroids. So, how does it work? I think all of us know puzzles, right? Those things. Puzzles, right? Now, if you try to fit this thing into this thing, it won't work. But if you have a different piece, then these two will work together. And that's basically the principle beyond the principle behind piece structures. Each structure is basically a box. So each structure is a box, and on the box edges there are points that say, okay, I'm connector number 5 going that way. I'm connector number 3 going that way. And as in the puzzles, this can be 1, this can be 3, this can be 4, this can be 5. Number 3 got lost. Number 2 cannot connect to another number 2. It needs to go to a receptacle that is opposite of number 2. So let's call it -2. This could be -5. This could be -4. So let's say there's another box here that has a connector here that says -5 this way. Now the generator knows that these two connectors can be put together, so the other box is generated here. Now this other box has another connector here, 0. And there's another box here that has a 0 going this way. Now we can't really put this connector here because the directions are different. But we can rotate the piece by 90 degrees, and then it will fit here. So basically the piece structure generator works like this. all of this has been in the top-down view. So it connects connectors that go together real well. It can rotate pieces so that the connectors fit directionally, and for each for each piece, we can further we can specify how it connects, because sometimes, such as for nether fortresses, they like a big house, then bridge, and a tower. So for the bridge, each piece of the bridge is one piece. But we say the bridge likes to connect to itself. So the piece knows, if I'm connected to myself, make it more often. So each piece has metadata, I guess, that says how often to connect. How often to connect if same? So if I'm connecting to myself, do I change this? What's it called? No behavior. The amount of randomness. No idea. Okay, so we call it weight. So each piece has a different weight, and if the more weight it has, the more likely it is to be chosen by the generator. So the generator has like 30 pieces, each has a connector of 0. So it calculates the weights and then says, okay, this one has weight of 1000, this one has weight of 1. So let's take the 1000 one. So the metadata can specify what adjustments to the weight are to be done based on if the piece is the same, or how deep it is in the generator tree. Because if you look at this, this is the base piece, the first one placed, and then there's a tree, really, because this one was second, this one was third, then there's another one through here. So it's basically a tree in the topological sense. Let's say there's one here, and based on the level inside the tree, we can adjust the weights as well. That's actually used for the nether fortresses, so that the bridges don't go forever. Okay. Now the piece structures. The pieces can be either predefined in Cuberite, which was the case with villages. We had each house defined in a Cuberite source. We also had other finishers that were using the same principles, such as underwater base and nether fortresses. Or we recently started having these pieces loaded from a file. And that's where the CubeSet files come in. CubeSet. A CubeSet file basically contains a list of pieces like this, together with a metadata. And the CubeSet files can be exported directly from the gallery server, which I'm pretty sure you know about. Is the server where we build stuff to be included in the generator. So this is how it is included. All right. So that would be all the generators. I wanted to talk about speed improvements, but I'm afraid we have no time for that. So I guess okay. No problem with overtime. Okay, I'll say something about speed improvements then. a little bit. I've already talked about linear upscaling. You remember the 4 blocks being expanded into 16 blocks? That was a huge improvement in speed. That was like 5 to 10 times speed up in generator time, which is impressive. Another technique, let's say, let's get rid of this thing. One of the techniques that is most used in programming for speeding up things is caching. And Cuberite is no exception. We have cache for biomes, we have cache for Terran heights, Terran composition, and that's it. Terran shapes, right. We cache everything up until the finisher step. Why that is so important? Imagine we are calculating, let's say we have a village. Now, let's start with a tree. So here's our chunk that is being generated, and we have a tree here. So it goes into the other chunk. You need to check the other chunk, and in order to generate this chunk, we need its shape. In order to get this shape, we need to average. We are using the Biomol shape generator, so we need to average more chunks biome-wise. So we need biomes for all the neighbors. So we're still generating this chunk, but we're already generating a 5x5 area of biomes. Because the tree could be here, could be here, could be anywhere. One more. Right. So that's 5x5 biomes, 3x3 shapes, plus 1 finisher. And this is what it takes to generate one single chunk. That's crazy. So if we were to generate these 5x5 biomes over and over, let's say the next, usually we don't generate just one chunk. We generate this chunk and then we ask, get us this chunk and then this chunk. So what we could do is actually remember the biomes for all these chunks and reuse them. So if we generate this chunk and this chunk, so another row of biomes, so we would generate, in the naive approach, we would generate 25 biomes plus 25 biomes for the next chunk, 9 shape plus 9 shapes for the other chunk, 1 finisher plus 1 finisher. So that would be a lot of work. When we reuse the chunk, reuse the data, we generate 25 biomes, but then we only need to generate these 5 new ones, so 5 biomes. Then we generate 9 shapes, and only these 3 new shapes, so 3 shapes. We still need to generate the same finisher. So altogether, it's almost 2 times speed up just for 2 chunks. If we then generate a third chunk, you can do the math, right? Now, in order for cache to be any useful, it needs to have fast lookups, because it doesn't help remembering stuff if you can't remember it. really fast. One interesting thing about biome caching, if you use constant biome generator, the cache actually worsens the performance because it's easier to generate the biomes from scratch than to remember them. Naturally, because it's constant. So, in order to be able to remember, the first cache we implemented was simple vector. Okay, this doesn't work. This is simplified, but you know what I mean. Vector of biome data. Each biome generated would be added to this vector, and so data that the vector would be limited in size so that old data would be overwritten by new data because old ones are not used anymore. However, when the vector reached size of about 30 items, I think, maybe 60 items, the time to look up data in the vector became so large that actually generating the data from scratch was faster than the lookup. So what we did, we used the chunk grid and said, okay, we have even chunk and odd chunk, even chunk, odd chunk, even, odd. So we have, if it's an even chunk, look at vector 1. If it's an odd chunk, look in vector 2. So suddenly, all these 60 items were split into 30 items each. And the lookups were fast again. But of course, only twice as fast. So the next logical step would be not even odd, let's make 1, 2, 3, 4, 5, whatever. So that's what multi-cache is about. So multi-cache splits the amount of caching between individual chains, and each chain is short, which makes it fast. Okay. The next speed improvement that could be done, but isn't done yet, is integer-only math. I've already talked about noise generation in integers. That's fast, that's good, but we could extend this into more parts of the server. So that's sometimes for the future. Well, I think that's it. Thank you for the attention. Goodbye.